Our first speaker of the day is Dierk Schleicher, and he's going to tell us about finding polynomial roots using complex analysis, dynamical systems, and computer algebra. So take it away.
So thank you very much. Can you all hear me?
You're good.
Okay, very good. Yes.
We have to talk in a microphone, so you can't unless, yeah.
Okay. So good. Please interrupt me anytime there are questions or comments. I am, first of all, of course, very grateful to the organizers for inviting me here. And I would have been so happy to be in person in Pisa, and I was on my way. This was probably the most complicated travel that eventually never happened. So I have to speak here online. And so I have to thank the organizers and the audience for being patient with me and bearing with me. So I would like to report on a topic that can be phrased in very close connection to the title of the conference, Dynamical System. This is what it's all about, my main research, and system of equations, especially solving equations. You'll see some explicit equations later on. So the goal of this talk is to find roots of polynomials using various dynamical systems. And well, one of my Pisa friends, unfortunately, cannot be here, who is Dario Bini. He's one of the experts on how to actually do this in practice. And while there are various competing methods, he's pushing one and pushing another. And that's part of what I want to present today. So we start with finding roots of polynomials is the fundamental theorem. I call it the fundamental theorem for algebra. Since Gauss's time, we know that every polynomial in one variable over the complex numbers has as many roots as the degree predicts. So we know they exist. And we've also known for centuries that there's no closed formula that finds these roots. So we need to find them for all kinds of practical reasons. And we have to use iterative methods. Well, there's another negative result that no iterative method that is holomorphic in one variable is generally convergent. So general convergence is one of the main topics today. That means it converges to some root on an open dense subset of the complex plane for all polynomials. So at least that's a negative result in one variable. And part of the difficulty is, should we use one-dimensional or higher-dimensional methods? Somehow the general conclusion is higher-dimensional methods are better. But part of my message is this may be because we understand them less. So let me present some of the methods that are in practical use. Newton's method is kind of the grandfather of all methods. It's named after Newton because he took it from, I don't know, Cardano, who took it, and eventually the Egypt seemed to have used it already. So it's supposed to find one root at a time when it does. And part of my work is that as a one-dimensional dynamical system, we understand it quite well. It has a bad reputation because it's supposedly chaotic. Hey, but we love chaos. We know something about chaos. So this, meanwhile, has good theory and works well in practice. And so at the end of the talk, I will present something about Newton's method, some positive result. The Weierstrass and the Ehrlich-Abert methods are both methods that want to find all the roots at the same time. So you have a polynomial of degree d, and you iterate in d variables, and the d component supposedly should find all the roots in parallel. Both of these methods seem to work very well in practice and seem to converge. Well, for centuries, they have passed the test of time that they always work unless you're in a very special, like when you have symmetries. If a real polynomial and you have complex conjugate starting points, you cannot get away from those. But other than this, Dario Bini, he's a proponent of the Ehrlich-Abert method, and he has great implementations to show that they essentially always work. Well, part of my message is that, well, it's not quite so. They work because we don't understand them, but the better we understand them, the more difficulty they have. So these are methods where you iterate in one or several complex variables. There are, of course, many other methods that seem to have good theory or work well in practice, but I don't want to go into all of them. In any case, so the ones that we are discussing today, these three, are dynamical systems in heavy practical use, and well, a big challenge to understand those. So there is this famous motto, what is the difference between theory and practice? And the answer is, there isn't one in theory. In practice, sometimes it's not quite so easy. And this is what I want to present. So we have the three methods by Newton, Weierstrass, and Ehrlich-Arbeit. Locally, they're all very well known, and globally, we know not as much about it. And so understand dynamical systems globally, well, you'll see. And as I said, general convergence or almost always convergence, that's the big question. There's some of the results I want to present. One reasonably new from my team, especially I want to mention my meanwhile postdoc Bernhard Reinke, that the Weierstrass method is not generally convergent against common wisdom of the practitioners. Weierstrass and Ehrlich-Arbeit moreover have orbits that are always defined. You can keep iterating all the time. And they converge, but they converge to something that is not a root. For instance, they could converge to infinity. That's something that was not known before and something that does not happen for Newton. We have good reasons to believe that Ehrlich-Arbeit is not a generally convergent system either, but at this time it's too complicated to prove this. So for the methods that work best, Weierstrass and Ehrlich-Arbeit, there's no global theory for the dynamics. And similarly, I'll present a method that I call iterative refinement. That again is a very efficient method. And again, we have no global theory for it. And finally, we can compare the two fastest methods, Newton and Ehrlich-Arbeit, which one works better. So let me start from the very beginnings. And as I said, please ask questions if you have any. The Newton's method, I learned it in high school, is if you have any differentiable map in one or many variables. This is the famous equation that works all the time. So the idea is if you have a map F which is differentiable, the meaning of differentiable means you can approximate it well by a linear map. And then Newton's method tries to solve the linear map. That is this approximation. So when you're close to a root, then this is usually a very good approximation. And if you have a simple root, then you double the digits in every step. So that's good. But globally, so this is one of my favorite pictures in degree 7, and the different colors show which of the 7 roots you're converging to. So it's known to be rather complicated and rather uninviting. How can you make sense of all this? Well, even if Newton is good to find a single root at a time, our goal is to find all the roots at the same time, even when the degree of the polynomial is 1,000,000 or perhaps even 1,000,000,000. So just finding a few points that find a few roots, we want to find all of them at the same time. So if you have many starting points that you want to iterate, you might converge to the same root rather than finding them all. So Newton's method is very classical. The Weierstrass method, well, often it's called the Durand-Kerner method. It's been reinvented by various people, but originally it's due to Weierstrass 130 years ago or so. So we have a polynomial. We know the roots exist. Of course, we don't know them. And Z1 through ZD is a vector of points that wants to converge as a vector to a vector of the roots. Now, in each component, say the ith component, we take the polynomial and divide out the linear factors z minus zj for all but the ith one. So it's a bit like in a calculus class, everyone thinks all the others presumably know what they're doing. So here, all the zi think that all the other zj know what they're doing. So if the zj are close to some other roots, then you divide it out. And what's left, so if zj is close to alpha j, Then what's left is something that's close to a linear map z minus alpha I. So you factor out, presume the other z approximations are very good, you divide them out and get something that's close to being linear. So, and then Weierstrass simply solves this linear equation for alpha I, and that's this. So you subtract, and if all the other roots are perfect at the location, it finds the remaining root on the nose. Ehrlich-Arbeit is a little bit more elaborate, and again thinks that this quotient is close to z minus alpha I, but a function that's close, well, this is a Newton step. You do one more Newton iteration on something that's close, and again, you hope that in this variable, you converge closer to the remaining root. So you can update all the, if d components, you do this in each of the d components in the vector, you can do this in parallel, then this is an iteration in d complex variables. This is the Jacobi style update. Or you can update, anytime you update one variable, then you use the new value already for all the others. And this is a Gauss-Seidel style update scheme. Both are in practical use and both have their advantages. Gauss-Seidel is a little harder to analyze because it's not really an iteration. And when you have parallel computing, it may not be the best thing to do anyway. So let me connect these two methods, Weierstrass on the next slide, Ehrlich-Arbeit. Let me tell you a little bit about their connection to Newton. So suppose the polynomial p is presented in coefficient form. I want to stress that finding roots of a polynomial, we don't have the polynomial given in coefficient form. It can be given any way we like, as a black box essentially. But suppose, I mean, it has a coefficient form. And if you know the coefficients, we want to find the alpha I. So from the, if you have the alpha I, then just multiplying out, from the root vector, you find the coefficients. It's just the elementary symmetric functions. What we need to do is the inverse, knowing the coefficients, how to find the root. So these are d equations and d variables if the polynomial is monic. And it's natural to use Newton's method in d variables to approximate from the AI to approximate the root. And that's exactly what Weierstrass does. So this is one more motivation for the Weierstrass method. One conclusion you can draw from it, that there's always an invariant hyperplane. So the sum of all the components in the approximation, the zi vector, the sum of these components is always constant. So Weierstrass keeps this hyperplane invariant and projects to it. So it's really an iteration in only d minus 1 variables. So one of the reasons why Weierstrass is somewhat easier to understand. Ehrlich-Arbeit is the somewhat more complicated method, but it has an interesting interpretation also. We can write Newton's method really as the sum of these linear factors z minus, and this is just the partial fraction decomposition of p prime over p. So you have the sum over the inverses. You don't know where the roots are, but you can still see the sum here. And that has an electrostatic interpretation. We put test charges at the alpha I, and then this creates some kind of electrostatic field. And in this electrostatic field, we see the field generated by the roots. And this is the inverse of the electrostatic field, the Newton displacement, how much you go. So when you're very close to a root, the field is big, and then the displacement is small because you're already close to a root. And now this is Newton. And Ehrlich-Arbeit looks very much the same. You have in every coordinate zk, you have, this is still the same thing that you have for Newton, and you add a term. So this is the electrostatic field you find for the roots, and this is the electrostatic field from all the other starting points. So you have positive test charges at the roots and negative test charges at the other approximations. So when some of them are very close to a root, the field cancels out. And then, so it's the Newton's method in which you suppress those roots that are close by, they're close approximated. So again, it's a very natural method. And in practice, it works very well. Ask Dario Bini, he has this MP-solve implementation that works very, very efficiently. And many years ago, I was in Pisa. We presented our Newton results that are coming a bit later. We presented these to him, and he asked us, okay, very good what you have about theory for Newton's method. Can you also do some theory for Weierstrass or Ehrlich Arbeit? So what I'm presenting to you in a way is motivated, inspired by my first visit to Pisa a couple of years ago. So locally, we know a lot. Globally, we don't do as much. So if you fixed points for Newton's method are exactly the points where you have the roots. So fixed points, roots are attracting fixed points, and all fixed points in C are roots. For the higher dimensional methods, if you have some of the components in this approximation vector is a root, then all these components will stay fixed, and you iterate really in lower dimensions for the remaining components. Like in Ehrlich Arbeit, as I said, these approximations just cancel the field coming from the roots, and that cancels out. And if all the components are at roots, then you have a fixed point in D variables. And in all these cases, these fixed points are attracting. So when you're sufficiently near these fixed points, you will converge to these fixed points. And you converge very fast. Usually it's quadratic, so the number of valid digits doubles on every step. And the Ehrlich Arbeit method is even cubic. So locally, it's all very nice. Once you're near the roots, then you're sure to find all of them very quickly, at least when the roots are simple. Globally, we know much less. Where do we have to start in order to be sure to find the roots, and how many iterations are required? So what is the computational complexity? So some problems have been known globally, previously for the global dynamics. One thing that I mentioned earlier is symmetry. If you have real polynomials with non-real roots, and you start the approximation with real starting vectors, there is no chance you can converge because, well, symmetry will always be preserved and convergence must fail. But apparently for the numerics people, so this is known, but this is known as a rather special case, and you avoid it by not starting on the symmetry locus. And then they say, it always works. And well, the test of time, more than 100 years, has shown that apparently this is so. In theory, there is another complicated problem that base and boundaries the base and boundaries must exist so that when you take your starting point and then want to converge to some roots, you can have a permutation and then it converges to some other root. So in the locus of CD, there are open sets that converge to different permutations of the roots. So there must be boundaries, and when you're on the boundary, they have no chance to converge. And it's surprising but true that these base and boundaries may have positive measure. They may have no interior, but with positive probability, you may randomly hit a boundary point, and then at least theoretically, you will never converge to a root. Well, and then there's the issue of infinity. For Newton, you can have orbits that can jump to infinity for Newton, or for the higher dimensional methods, there are points of indeterminacy, so that after some number of iterations, the iteration may fail to be defined further on. So all this has been known, except perhaps positive measure is a relatively recent observation coming from one-dimensional dynamics. Nonetheless, empirically, the methods Well, they may work, but there's some empirical problems too. Even Steve Smale, perhaps earliest, discovered that they're very simple, even cubic polynomials like this one, that have attracting orbits. So that is an orbit of higher period, which is attracting, so it's stable under all kinds of perturbations, where the dynamics converges to periodic cycles, but not to roots. The Newton's method is not generally convergent, and that is well known meanwhile. So if you look at this cubic polynomial, you have the three roots, red, green, and blue, and you see some black dots here. There's a little zoom. It's a zoom of pretty much this area. So there are some black dots.
Dierk,
yes.
Can I ask a question?
Sure.
Yeah, so it's the precise meaning of not generally convergent. Is that there's an open set of bad initial starting points.
For an open set of polynomials.
Okay, thanks.
So the precise definition, general convergence means, well, one way of saying it, every polynomial has an there's an open dense of initial points that work well for every polynomial. And that's what you want to have. Mm-hmm. Except you don't get it.
I see.
And
yeah.
The counterexample is this: there is a super attracting two cycle, so an open set that cannot converge, and that's stable. Is an open set here. It's stable under perturbation as an attracting cycle. So nearby polynomials will have the same problem. So this is not a particular exceptionally bad polynomial. Perturbations have essentially the same property. So the problem is an open set in dynamics cross parameter space.
Got it.
Okay, so I appreciate questions, and I hope not only the session chair will ask any, but others if they wish to.
Session chair's got the microphone, so other people have to work harder, but I'll let you know.
Well, I'm sure the chair will make it easy to solve that problem.
I'll do my best.
Very good. So this is one problem. Another is, if you want to find d roots, so you have to have at least d starting points and d orbits that converge. It's difficult to correlate those. You can just start at d different points, but they might all converge to the same root, or some to the same and some to different ones. But there might be some roots which seem to be hard to find. Some orbits might converge to attracting cycles, and others may all converge to the same. What I do not want to use is deflation. People often suggest this. That means you find half the roots, you divide them out, and then you have a lower degree polynomial. But that is numerically not stable, and often polynomials are given in very nice form, and by deflation, this all breaks down. So the goal is to find them all in the first shot. And this has worked for degrees a million and even a billion. So can I zoom here? Yes. I want to show you this diagram. And you hope you agree that this is as constant a graph as they possibly get. What does this do? This is a family of polynomials of degree 2 to the 10, 2 to the 20, up to 2 to the 30. 2 to the 30 is more than a billion. And these polynomials have been solved by an adaptation of Newton's method that we call the iterated refinement method. All the roots, all the 2 to the 30 roots have been found, with a proof that they have been found. And this diagram shows the number of iterations scaled. Of course, it has to scale with the degree. It's the combined number of iterations to find all the d roots. So it has to scale with d. And then the loss factor is log d to the power 1.1. And then this is the experimental graph. And the coefficient in front is 35. It's not a billion, it's just a very small constant number in front. So this is an experimental result that in good cases, Newton actually does work, despite all these problems.
Dierk, I ought to disguise my voice or something, so you think it's someone else. But so I'm puzzled about something with these really high degree polynomials. If you, I'm just imagining that if you've got a polynomial of degree 1,000,000 and you change one coefficient even slightly, that many of the roots jump all over the place, so that most of them are not stable enough to have any real meaning.
That is an issue that everyone brings up, and you can have it not only for degree 1,000,000, but even for degree 20.
Mm-hmm.
So the famous polynomials that do that. Yes, you have to deal with this issue. I am not an expert in evaluation of polynomials. Well, my work is on finding the roots, provided you can evaluate the polynomials easily. So this is the family of polynomials that's given by iteration, which is more easy. They're still, I mean, all these polynomials are very ill-conditioned. We have to admit that. And this is what you're referring to. They're ill-conditioned.
Right, right. Yeah, and you can just work with lots of digits of accuracy and deal with it. But that's, I don't know, that doesn't seem real in any sense. I'm sorry, I guess I'm asking a question that
this is a big question, absolutely. There are various answers. One is, these are difficulties and it works anyway. I mean, the polynomial is given, it has roots, and those you want to find. What we do is have polynomials with integer coefficients, so that at least the evaluation, well, of course, you work with complex arguments, but the coefficient evaluation you can do more efficiently. And then you do it by iteration. So that the one selection we made is for polynomials that are easy to evaluate.
Mm-hmm.
They're not given in coefficient form. If you look at the polynomial, some of the coefficients have the size 2 to the 2 to the 30, which is bigger than anything you could ever store. So, but partly this is if you want to evaluate the polynomials in coefficients, and then the answer is don't.
Okay, sorry, I'll let you continue.
This is a real issue that I'm aware of. And you have to find a way around it.
What do you mean by saying that the polynomials are given by iteration?
So one famous set of polynomials that was independently a demo polynomial for Dario Bini's MP-solve and for us is polynomials of the form c squared plus c squared plus c squared plus c. And you do this so many times. So when you iterate this n times, you have a polynomial of degree 2 to the n. Makes sense. And the coefficients are all integers. So with 20 iterations of this thing, you have a polynomial of degree 2 to the 20, which is 1,000,000. Does this answer your question? Of course, you can modify this in various ways. These happen to be known as the Mandelbrot-Center polynomials, but it doesn't matter. You can modify this anyway. You get a family of polynomials that is extremely ill-conditioned, but that can be evaluated efficiently.
I think we got it.
Okay, thank you.
Maybe not.
Oh.
So you're iterating a fixed polynomial, so the dynamics don't change, and the roots are the inverse images of the roots of the starting polynomial.
Well, you cannot find in this thing, you cannot find the roots by inverse iteration. In some easy configuration, perhaps, but if you will, just to make it more confusing, if this is something funny, which is just random, then you can no longer take inverse iterations.
I think I've got it now, thanks.
Okay. So, Weierstrass and Ehrlich Arbeit are really, I mean, I will say something critical about the theory, but in practice, they really work like a charm. They've passed the test of time over decades, if not centuries, in uncounted experiments. And ehrlich Arbeit, as I said, is the standard implementation for MP-solve, which has been used so many times and always worked very well. And recently, Dario Bini and friends have improved this specifically for the polynomials where we were beating. So we were beating them with high school students on their demo polynomials. And that was, well, they got me the invitation to Pisa, and it was an encouragement for them to improve. So recently they've updated this to degrees, also up to billions. So they really work well. And there are reasons why they're so efficient. Now let me move to what can be wrong. As I said, the main problem, at least among the known problems, are attracting cycles. So we have a periodic orbit, period 2 or higher, for which a neighborhood converges to the periodic orbits. The roots are the periodic orbits of period 1. Higher periods are bad, and still they could be attracting. So differentiability means we can test this by linear algebra. You have a differentiable map in several variables. You have a fixed point. And the Jacobi matrix has all eigenvalues on the unit disk. Then this fixed point is attracting. So it attracts the whole neighborhood to this fixed point. So K, the dimension which we iterate, is 1 for the Newton method, and Weierstrass ehrlich Arbeit iterate in the full D-dimensional space. So specifically, if F is the Newton method, the Weierstrass ehrlich Arbeit, so if F has a fixed point, the fixed point is attracting, and this is good. But if F is an iterate, so the third iterate has a fixed point, which is not a fixed point of the original map, then we have an attracting cycle. And this attracting cycle attracts a whole neighborhood and is stable under perturbation. So attracting cycles certainly spoil general convergence. So that is the thing that, well, in the sense that we are after for negative results. If you have several variables and only some of the eigenvalues are in the disk, so are less than 1, then there is so if m eigenvalues in the disk, then, well, standard result is that there is an invariant m-dimensional complex manifold, the stable manifold to this fixed point, on which the orbits converge to this cycle. And this stable manifold is tangent to the eigenvectors predicted here from linear algebra. So then you have something which is not attracting on an open set of CD, but it's semi-attracting that you have a complex manifold in which you converge to this fixed point. So does this happen, or can you expect this to happen? Well, the upshot is yes, it does happen. But let's see what we can, just by dimension counting, what can we expect this to happen? So we have monic polynomials of degree d. This is a d-dimensional space. We can parameterize it by the coefficients or by the roots. There are always d of them. But all these 3 methods respect affine coordinate changes. So if you translate the roots, then the whole dynamical system is translated. And if you scale the roots, again, it's the dynamics is scaled. So the dynamics is really conjugate to the original one, up to affine coordinate changes. So the true parameter space is d minus 2 dimensional for all the methods. So quadratic polynomials are usually trivial. And the first interesting case are cubic polynomials. So we can use the affine freedom to move one root to the origin, the second root to 1, and then the third root is wherever it is. And the third root parameterizes the polynomials. So for cubic polynomials, the parameter space for all the methods is really the complex plane. And cubic is the fundamental case in which you can see everything most easily. So the periodic points satisfy algebraic equations. Well, you can, for instance, parameterize like so. Periodic points satisfy algebraic equations. And so the eigenvalues themselves are algebraic functions. And then these, for Weierstrass, are two eigenvalues. For Ehrlich Arbeit, there are three. You want these eigenvalues to be in the unit disk, or maybe you don't want them in unit disk. In any case, that's the interesting question. So the question of attracting cycles really becomes a real algebraic question. So we're moving from numerical analysis via dynamical systems to algebra, specifically real algebra. So for Newton, for cubic Newton, the dimension count is the easiest. We have a one-dimensional parameter space. And the eigenvalue of periodic point is a one-dimensional function, which depends on one variable. So holomorphic functions in one variable must be take images that are dense, so there must be attracting cycles of all periods, just by dimension counting reasons. And here they are. So this is one of the beautiful fundamental results by Doherty and Hubbard from the 80s. We parameterize the cubic polynomials again so that the roots are at 0, 1, and then lambda. And then for every period n, there are parameters that have attracting cycles of any period. And if you want to find them, this is the parameter space of Newton's method. So this is the lambda plane. And whatever the colors mean, there is some black here, and this is a blow up. Black means you have attracting cycles of higher periods. And you know, this is the famous Mandelbrot set here. So in other words, it's a theorem that the set of parameters in lambda for which you have an attracting cycle is organized in the form of finitely many homeomorphic copies of the Mandelbrot set. So all the bad or interesting cubic polynomials are organized. Whenever the attracting cycles happen, you have to find little homeomorphic copies of the Mandelbrot set. No matter how complicated the Mandelbrot set is, all the complications are embedded here in this fundamental problem of general convergence, of failure of general convergence, of Newton's method, even for cubic polynomials. So even to understand Newton's method for cubic polynomials, you really have to understand the Mandelbrot set. So this is old news, so to speak. Let's move to cubic Weierstrass, which is not quite so old news. If we talk about cubic polynomials, we still have one parameter lambda that parameterizes the roots. And we have three eigenvalues because we iterate in three variables. So generically, we would expect semi-attracting cycles. That means one attracting direction, not necessarily all three. But here for Weierstrass, the dynamics projects to an invariant hyperplane one-dimensionless. So we really iterate in two variables. And one eigenvalue is 0 just coming from projection. So two eigenvalues remain. And for every period, there is no a priori reason why both eigenvalues can simultaneously be of the two remaining eigenvalues, whether they can be simultaneously in the disk or not. On the one hand, Stephen Smale, from the dynamical systems point of view, has conjectured that there should be attracting cycles. And that conjecture, again, is 30 or 40 years old. On the other hand, there's the common wisdom by the numerical analysts. If there were any attracting cycles, they would have been found experimentally decades ago, long ago, because open sets you find eventually. So, and then Bernhard Reinke came and said, well, let's look at this algebraically. Both eigenvalues are algebraic functions on the same surface, in this case, on the same lambda plane. They must satisfy an algebraic relation given by polynomials. So now we move the whole question to algebra, and then he's good at computer algebra. So what we cannot do by hand, let's do this with computer algebra. And here's the result. The Weierstrass method is not generally convergent. More precisely, for every degree 3 or bigger, the Weierstrass iteration for this has attracting cycles of period 4. And period 4 is minimal. There are maps which have no attracting cycles which may have no attracting cycles of lower periods, but period 4 is always guaranteed. So this settles this decade-long dispute between numerical analysis and computer algebra. Numerical analysis and Stephen's mail by methods of computer algebra. Bernhard also discovered another thing, that all these methods have orbits that I mentioned earlier that are defined forever, and that they converge, but they converge to infinity or somewhere else. So convergence is good, but convergence to infinity is not so good. As I said, this works because we have a big march quite across some areas of mathematics. So let me tell you something about Bernhard's proof strategy here. In the setting of algebra, well, this is a workshop on systems of equations. I'm working towards developing some systems of equations here. So it looks complicated, but really it's not. It's the space, you pick a polynomial and you pick a point z that is periodic of period, of whichever fixed period n, for the Weierstrass method. So for every polynomial in every period, you expect that there are finitely many such vectors. So this is really a variety of dimension d that generally of dimension d. For each of those, which is d-dimensional, there is you can pick the periodic points. And Mn adds to this the d coefficients, which are the eigenvalues. So if you know p and z, then you also know the eigenvalues, up to permutation perhaps. So both of these are d-dimensional varieties. And this periodic point z is attracting if all the mu I are an absolute value less than 1. In other words, there is a natural projection from this variety here to the d eigenvalue coefficients. And this projection, if it intersects the unit disk and d variables, that exactly means that you have an attracting cycles. So the idea is that with computer algebra, we find explicit equations for all these sets and for the projection. And then we check where they are. In some cases, so again, we have this variety here that tells the polynomial, periodic point, and the eigenvalues. As I said, these are d-dimensional varieties. But by affine equivalence, we really lose 2 dimensions that don't change the eigenvalues. So it's a map from d-2 variables from d-2 dimensions into d dimensions. And it's not clear that such a map has to intersect the unit disk. So we are missing 2 dimensions, well, except for Weierstrass, because one eigenvalue is already 0, we only miss 1 dimension. Still, nothing is guaranteed. So for cubic polynomials, we have 1 parameter dimension, 2 eigenvalues for Weierstrass. And this is simple enough that we can actually do this using computer algebra. We have curves, 1-dimensional curves in C2, each defined by a single equation. And here they are. Weierstrass, 1 variable, two eigenvalues, and they always satisfy this equation. This is something you can even verify by hand. This is the product mu1 times mu2 minus 2 times the sum plus 6 must be 0 if you have a periodic point. Now this is, if it were to be in the unit disk, this is less than 1, this is less than 4, so the sum is at most 5, plus 6, it can never be 0. So this is an algebra proof that Weierstrass for cubic polynomials never has attracting cycles of period 2. If you have period 3 in the special case that you have some permutation, this periodic point it's permuted under the dynamics, you get a similar equation that the sum of 2 fluid powers, the sum is -3. So again, they cannot both be in the unit disk. And after this, we thought, oh, maybe this is a beginning of an algebraic proof that Weierstrass could perhaps be generally convergent. Well, so far so easy. I will not read this equation. But hey, we're talking about equations, and now this is computer algebra at its best, and perhaps even close to at the current limit. Now we're looking for 3 cycles for cubic Newton maps. And well, whatever it is, we have explicit equations coming out of the computer system. And it's not something you would have guessed sort of ahead of time. But if you have this equation, you can check again, no 3 cycle can be attracting. So Weierstrass for cubics has no attracting 3 cycles. And this is pretty much, it's heavy lifting with computer algebra. And it's pretty much the limit of what you can possibly reach. And then, so this is almost the end of the story. Except then we discovered in period 4, the general period 4 is far out of reach. But you can have periodic cycles which have special points so that the second iterate is a permutation. So first, some periodic point goes somewhere else, and then comes the periodic permutation, and then so it's a 4th cycle. So the second iterate just permutes those 2, keeps the third fixed. So when you do this again, 2 more times, then you're back. You have a periodic 4 point, and so this gives you a relatively mild equation compared to the general period 4. And this time, computer algebra tells us, oh, there is an attracting cycle. Again, not something you would necessarily see by hand. And this is the dynamical plane in the, well, this is the real projection of the dynamics. And the colored points are the ones where you indeed you find attracting slices. So this is the polynomial z cubed plus z plus, well, this is the best one, but you can take 178 or 175 or so, and you still have an attracting cycle for this cubic polynomial. So Smell was right, and the numerics people weren't looking carefully enough. And then the phenomenon is reasonably small. So this is z cubed plus z plus t. And t as well, 177 is the best, but between 160 and 180, there is this shape in which you find attracting 4 cycles of permutation type. And bifurcating from this, you have attracting 4 cycles of general type. So that once you know where to look, you find them quite well. It's very small in parameter space, and it's very small in the dynamical plane. So the product is not easy to find, but computer algebra helps us. So Weierstrass fails to be generally convergent. And then the next question is, how about Ehrlich-Arbeit? Now, there are 3 reasons why Ehrlich-Arbeit is more complicated. Well, why this is harder to do. One is that the map itself is more complicated. The second problem is that Ehrlich-Arbeit, Newton, remember, has a codimension 1 hyperplane on which everything projects, which yields simplifications. Ehrlich-Arbeit does not do this. So we have not 2, but 3 non-trivial eigenvalues, even for cubics. And the third is actually a good reason. Ehrlich-Arbeit is not only invariant under affine maps, but under all Möbius maps. So it has a 3-dimensional conjugation rather than 2-dimensional. So really, all the cubic polynomials with all simple roots, they're all the same for Ehrlich-Arbeit. So there's only one of those. So in order to have an interesting space of polynomials, you have to go to degree 4 for the polynomials, which means you have 4 eigenvalues to consider, as opposed to 2 for Weierstrass. So life is much more complicated, and current day computer algebra is just not ready to handle this heavy lifting that's required at this point. So it's hard to find numerically, but conceptually, we feel there should be every reason why Ehrlich-Arbeit should be just as non-generally convergent as Weierstrass is. So let's move to in the last, well, a few more minutes, I think I have. Let me mention another result, which is related, for which you can prove something. Remember, attracting cycles is when all the eigenvalues are less than 1, and semi-attracting is when some eigenvalues are less than 1, then we get invariant manifolds. So again, led by the pioneer work of Bernhard, we have every polynomial of degree at least 3 with distinct roots. There are vectors where you start, you can iterate all the time, where the Weierstrass method converges off to infinity, also for Ehrlich-Arbeit. The way he does that is that the Weierstrass method was not only defined on C2, but he can also extend it to infinity. There's a hyperplane at infinity. Well, so you can extend it to the compactification on the P2, complex P2, and it has an explicit form. So at infinity, you have a line, a Riemann sphere at infinity, and you have a dynamical system, which is always the same for all cubic polynomials. So you can iterate at infinity, which is not something you would find numerically interesting. But at infinity, you have periodic points, and the periodic points may be repelling in the direction of infinity, but it's attracting in the reverse direction. So it has an attracting an invariant manifold from infinity that reaches into C2. So, and the project in C2, there is part of this invariant manifold on which you must converge off to infinity for purely algebraic reasons. So therefore, you must have orbits that go to infinity for all the methods and for all the degrees. So that was the Jacobi variant when you update all the coordinates at the same time. But as I said earlier, you can always, whenever you update one coordinate, you can also use this immediately and still have. So this is fast and numerically if you have one computing core, but the same problems happen even under Gauss-Seidel. You have orbits that converge off to infinity. So all these results are really results that you first prove for cubic polynomials, but then it's easy to upgrade it from degree 3 to all higher degrees. So this is a table of what happens for the various methods. Newton, Weierstrass, Ehrlich-Arbeit, and then Weierstrass and Ehrlich-Arbeit also in the Gauss-Seidel update. You can count what is the dimension of parameter space. It's d minus 2 dimension. For Newton and Weierstrass, and Ehrlich-Arbeit is d minus 3. You have the dynamics. Newton is in one variable, Weierstrass is d minus 1, and all the other methods iterate in d variables. So it was known that you have attracting cycles for Newton. Now we know this is true for Weierstrass. Also, the colored results are the new ones. And here we believe they exist, but we cannot prove it. Diverging orbits that iterate and then converge to infinity do not exist for Newton, but they exist for most of the other methods. And the failure of general convergence, what was known for Newton, is now known for Weierstrass, and we believe, well, it's the same as attracting cycles, presumably. So these are the negative results for Weierstrass and Ehrlich-Arbeit. They seem to work well, but we don't have any global theory except what I presented earlier. We don't know much about the global theory about Weierstrass and Ehrlich-Arbeit, but there are quite some positive results on Newton's method. And that is something, if I have a few minutes in the end, I would like to move to a little bit of Newton, especially since what we worked on Newton, that got me into the connection with the numerical root finding people, Dario Bini in Pisa and Victor Pan in New York. And well, they were asking for the global results. And well, they unfortunately only got negative results, but at least something they did get. So let me spend a few last minutes on Newton's method to show what is possible, especially in the view that people say, well, we know so much about Newton that's bad, So let's use something else like Weierstrass. Well, unfortunately, we think Weierstrass is good or ehrlich, aber because we know little about it. And if we learn more about it, probably all the other problems would exist just as well. So meanwhile, rather old news is that we have a good set of starting points. If we put them for Newton in circles around the roots, then we proved some 20 years ago that if you have enough points, then depending only on the degree and some normalization, then you can be sure to find all the roots, iterating just plain Newton's method. It was originally, well, you need these starting points in order to find d roots. And then the fudge factor is really square of log d. And by probabilistic methods, you can turn the fudge factor to the square of log d. And well, how do they say log d is a function that theoretically is known to go to infinity, but in practice, it has never been observed. This is a very small number. So you can start with few points originally. So here's degree, I don't know, 50. And then the starting points, here's a zoom. You have to put them a little bit around, a few times 50, and you can be sure to find all the roots, even when, like here, you have attracting cycles. Even if you're interested only in real polynomials, here all the roots are on the real line. How many roots are there? There are a few nearby roots. It's hard to tell this apart by real methods. But complex tells you there are 1, 2, 3, 4 colors, so there must be 4 roots here. And so maybe let me skip this and just say, in Newton's method, we have good control for these d squared points. We have d squared points here, but they all do the same thing in areas where you have control. So you have d orbits, and each of them you have to iterate at least d times in order for something interesting to happen. So you waste on this area, you waste d squared iterations. And then if you have complexity d squared, which is what we can get, this is best possible, but wasteful. And now the idea of the iterated refinement method is that out here you only take some representative orbits where you know what happens, and you refine it only in between when things get more interesting. And this is how you got the complexity of essentially log linear. Here, this is the iterated refinement. You start with 64 orbits, and as necessary, you iterate as soon as the orbits are no longer doing the same thing. This is a heuristic method, but this is the method where you get degree abelian by a high school student on a student laptop. So let me conclude now. Root finding is classical and important. Some people even find, like dynamical systems people that are statistical physics people, they need all the roots for very high degree polynomials. There's a big gap between theory and practice. The methods that are predicted to be working well in theory and those that work in practice are different methods, except Newton seems to work well. It has a poor reputation, except locally. But meanwhile, it has a good theory and it's very good in practice. Well, sorry, my friends, for Weierstrass and ehrlich Arbeit, they have a very good reputation. But as soon as you do develop theory, you discover that they have the same problems that are known for Newton's method. In any case, these are very interesting dynamical systems. And hey, using computer algebra, you can do things and settle questions that have been open for decades or perhaps even a century. There are many more questions on all these topics that are still wide open. Thank you very much for your attention.
Thank you. Are there any questions for Dierk?
In the cases, a very interesting talk, by the way. Thank you. In the cases where there are divergent orbits, has it been observed that you can take longer and longer to find the roots when you do? I mean, if you have these methods, presumably sometimes they should shadow the stable manifold of infinity for a long time before winding back and actually converging to the roots.
So what exactly was the question?
when you, in these cases where presumably you'll almost always see convergence, is the time going to infinity?
Yes. So whether these have ever been observed in practice?
Yes.
I don't think so. Because this is numerically, if you're in a complex hyperplane, in theory, numerical inaccuracy will always kick you a little bit off this hyperplane. And it's repelling in the opposite direction. So theory predicts that you will not, with a round of errors, you will not stay on the plane. Of course, then there is a shadowing theorem that you say, well, by shadowing, you might find them. This is not something you would expect in practice. So this is an issue that does exist and is known to exist, but is not an issue that worries the theory, the practitioners. Like the issue that Weierstrass, I didn't mention this too much, the Weierstrass and Ehrliche Arbeit have points of indeterminacy, which are again complex hyperplanes where the iteration is not defined. So when two components become equal, it fails to be defined anymore. That's what happens in complex higher codimensional spaces is not of relevance to the practical people. So I don't think you would expect to see any of this in practice. It's an interesting property from a dynamical system. And well, Weierstrass's method is 130 years old. Nobody saw this. I think somebody tried to prove it. This is not something numerics people would happen to find. Attracting cycles, they would find. Well, they are rare, it seems. But this is practical relevance. Divergence to infinity is a nice theoretical feature, but not something that happens in practice. And I think one should be able to prove, we discussed this, that the probability for a random point to go off to infinity is 0.
Thank you. Hi, this is probably an extremely naive question because I'm not I've never worked with Newton, any of these algorithms, but what is the situation for real polynomials? Is it everything is trivially fine, or do these problems arise even for one-dimensional real polynomials?
All these problems, so you can have real, so let me think. In principle, it should all be possible to have this for real polynomials too. Well, as I said, z cubed minus 2z plus 2, that old Newton example is a real polynomial.
So in the sense that these problems you've talked about, they arise already in the context of real one-dimensional polynomials. This is what you're saying?
Yes.
Okay.
But on top of this, so let me go back to the, here, this is the real problem. Finding, even if all the roots are real, you want to find them all. Maybe for Newton, the biggest, in reality, attracting cycles except for Newton, you find them by coincidence. This polynomial was found just by coincidence. But it's not something that in practice happens very often. But the difficulty for real polynomials in Newton is to find all the roots. If you take so many starting points, you want to find, we can take these starting points, you want to find all the roots. Well, chances are some find the same roots. So you need more than these starting points. And then how can you guarantee that you find all the roots? And that is a very serious issue, even for the reals.
I see.
You see,
So there's
these
still
roots,
open problems in that setting as well. These are open problems, even in that extremely.
well, for Newton, we have a theory on good starting points. We need d times log factors, and then we can guarantee even when the roots are very nearby for the real polynomials. So by just purely real methods, the graph would look a little bit like, how many real roots do you have here? It's hard to find them by real methods.
So, but what about just the question of convergence, as you said, absolutely convergence? Is that something that is always true in the
As I
real
said,
one dimension?
z cubed minus 2z plus 2 is as real as it gets. And it has an attracting 2 cycle.
Oh, sure. So does z squared plus c, right? So in that case,
No.
it's a problem.
No, well, the iteration of z squared plus c has attracting cycles, but the Newton method for quadratic polynomials is very simple. Newton method, so let me just draw here somehow across. This is a fully new picture. I need some space. So I have one root here, I have another root there. I divide the plane. Let me draw thicker. One root, the other root, you divide the plane symmetry. And then everything on the one side converges to the nearest root. So for quadratic polynomials, Newton's method works like a charm. But hey, it's only quadratic polynomials. As soon as you have cubic polynomials, even when they're reals, you can have attracting cycles for Newton's method.
Okay, thank you.
That was.
Okay, so I think there are other questions, but I want to make sure that we get in a coffee break for the next talk. So maybe
That's easier for me here. Yes, but I
yeah,
understand.
that's right. Yeah. So I'll leave the microphone on, but let's take this moment to thank Dierk again, and then we can all. There definitely is at least one other question, I think. So
I'm here. I have my coffee.
Hello. So would your analysis be affected if you use a damped Newton method? Because as far as I could see, you don't use damping.
No, right. Or relaxed Newton's method, right? So you have a relaxation factor. I think it's just the same.
It's just the same. Okay.
Yeah. So you can do the analysis. Well, the dimension count, as long as you have a fixed factor in front, the dimension count would be just the same.
Okay.
So this is something, yeah, if you want to do it, it's an interesting point from the dynamical point of view, but for somebody to just work on it, to sit down and cross the i's, dot the i's and cross the t's, it is just the same.
Okay.
So it's not necessarily a paper you want to spend time on because it's so natural and so obvious to do the same thing.
I see.
But if you have a master student who wants to work on it, then, well, or even a PhD student, it's not a big theorem to get, but it's something, it's a low-hanging fruit to reap.
Okay. And another question. So if you use a scientific platform like MATLAB, for example, and you want to compute roots of polynomials, univariate polynomials, probably what you would do is to construct a matrix whose eigenvalues are these roots, and this matrix can be expressed probably not in a monomial basis, but in a Chebyshev polynomial basis, and then you use numerical eigenvalue, matrix eigenvalue algorithm to find the roots. So that would be, for example, the QZ algorithm that would reduce your matrix to some canonical form. So as far as I understand it, this is a much more complicated dynamical system, but yeah, and as far as I know, this works for degrees by the millions as well. There are some papers reporting that. So
if you have a reference, let me know.
Okay,
so
I will.
When I've talked to numerics people, they always said, don't use Newton's, always use matrix methods, always use eigenvalue methods.
I see.
And then in the end, it turns out, oh yes, but it works for degrees a few hundred, because that's what people need in practice, I admit.
Yeah.
I've never seen a report for high degree polynomials for eigenvalue.
Okay, so I have a reference in mind. I will send it to you. Yeah, thank you.
I would be happy about it, but I would be surprised. Is there any theory about it? This is one of the methods that works well for moderate degrees.
Well, there is a theory of reduction to, I mean, canonical form matrices, which is what numerical analysis is about. It has been around for about 50 years. And of course, it's a non-symmetric eigenvalue problem. It's more difficult than the symmetric one. But I'm not an expert in numerical analysis, but I think there are a lot of results, numerical stability and things like that. but this is not from the dynamical system perspective, as I can see it.
Right. So
Yeah.
I'm not a numerical analyst.
Uh-huh.
And I would assume that they know it as stability. Locally, it should be stable. But I would be surprised if they had any global results.
Okay. Thank you.
But it happens to work like Weierstraß's ehrliche Arbeit. They have passed the test of time, yes. Okay, so this is what it is.
Okay. Thank you.
Okay.
Oh, there is still somebody else. No? Okay. So goodbye. Thanks for the talk.
Thank you.
All right, well, we're ready for the second talk of the morning here. Speaker is Turgay Bayraktar, and he's going to talk about expected topology of random real algebraic plane polynomial curves.
Oh, thanks for the introduction. I'd like to thank the organizers for inviting me to this conference and their hospitality. It looks like a real algebraic geometry talk, but mostly I'll be using complex analysis techniques. So the problems are coming from there, but the way we do will be complex analytic, hopefully. So to fix the notation, RPM will denote the real projective space, and CPM is the complex version of it. And we're interested in the real vector space of homogeneous polynomials in n+1 variables of degree n. Say f is one of them, then we look at the real zero locus, that is in RPM, and the complex zero locus, that is in CPM. We are interested in some of the geometric features of these quantities, like projective volume or topological features of the real one. For instance, number of connected components, or maybe higher beta numbers if you wish, and their distribution in the plane, particularly for algebraic curves, as the degree grows to infinity. So we want to talk about asymptotic results. In complex dimension one, or dimension one rather, this problem just corresponds to counting real zeros of polynomials, if you're talking about the connected number of connected components of this quantity. And the first one here is the fundamental theorem of algebra. And the second one is just saying that when the coefficients are real, roots are coming as conjugate pairs. Okay, so we know these things, but the question would be, which already appeared in Michael Schub's talk, how many real roots can a generic polynomial have? Okay, so the word generic stands here, whichever way you wish, but one approach to address this question is to put here random. Okay, so we will put a probability structure on the space of polynomials, and according to this probability structure for a randomly chosen polynomial, what's the expected number of real roots, etc. So those questions are we're interested in. Okay, the first model I have in mind is the standard. So it looks like a standard polynomial written in the monomial basis, except that the coefficients are random variables here that are chosen independently according to the standard real Gaussian and 0, 1. Okay, so the mean is 0, variance is 1. And so this induces a product probability measure on n+1 dimensional vector space. And according to this probability measure, we are choosing a random polynomial and counting the real roots. Okay, and we are interested in the statistics of this random variable. Okay, so this goes back to Mark Kutch. In 40s, what he proved that expected number of real roots for such polynomials has this density here, and the asymptotic expansion of this according to this degree grows like log n times 2 over pi. So this number is significantly lower than the degree n. Okay, and as you see, this function here has a lot of mass near -1 + 1, which basically indicates that the real roots are accumulating around the 2 points -1 and +1. Okay, so let's take a look at the proof of this argument, of this result. Well, let us denote this step function eta defined near the origin with the value 1/2 epsilon in an epsilon neighborhood of the origin. So first, what Hodge does, he looks at a random walk on the plane, and then you have a horizontal line, which is the x-axis, and you want to know how many times your random walk crosses this axis. So first writes down a counting lemma for this, but we have an advantage here. Remember, we have Gaussian polynomials, right? So having a double root is an algebraic condition, but we have a continuous probability measure, so it doesn't see this exceptional set. So probabilistically, generically speaking, the roots are simple. So you either cross this horizontal axis towards up or towards down. So that's why he concentrates on this. So near a root, because this lives near the origin, so this lives near the roots of Fn. So it just looks at how much the derivative changes, because you're crossing up or down, right? So you will just focus on this. And as epsilon goes to 0, this quantity basically counts the number of roots for a nice polynomial. But almost surely our polynomials are nice. So we have a counting lemma. And the idea is to randomize this. So basically, the idea is you want to compute the expectation of this. So you want to move the expectation inside with some theorems from integral theory, right? Like Fatou lemma, Lebesgue dominated convergence theorem, things like that. Okay, so then you need to compute the expected value of inside. So now we want to compute the expected value of inside. Okay, so let's introduce more notation. Basically, looking at these terms, so I'm going to write down the covariance matrix of these two Gaussian random variables. Okay, and I will denote its value. This is okay. So a random vector root, t is a real number, and I will look at the covariance matrix, which is defined in this way. Okay. And then this induces this joint distribution here. And computing the expectation, okay, so I just computed here, turns out to be this. And limiting this, because at the end, I know that I want to move the expectation inside and take the limit. So why don't we wait? Just do it here. So I will get this, okay, so after all this, I go back to what I wanted to do, and then using some theorems from analysis, move the expectation inside and move the limit outside. So this is what comes up. So this is how they did it in the first place. And then after this computation, there were some other results. So I want to now look at this very carefully. You could also obtain the same thing in the following way. If you denote your moment map, sort of 1 t to the n. So these are your basis elements evaluated at the point t. This quantity inside is actually this mixed derivative of the log of this inner product. This is just a standard inner product on our n plus 1. Evaluated at the diagonal, and then first you take the mixed derivative and evaluate it at the diagonal. It turns out to be that's equal to this, and you arrive to the last line. So this is, I think, how Rice wrote it down in his works. So this is basically the same calculation. Basically can be obtained as the conditional expectation of the derivative at the point t, given that the function vanishes. Okay, so how so why I did this calculation, where this comes from? I mean, in the first place, why I did that, I looked at this thing. The answer was in this paper by Adelman and Colston. They gave a sort of a geometric proof of the same sort of thing by using Craftston's formula. So how does it work? So this is your random vector, which involves the random coefficients. If you normalize it by dividing its norm, this is a unit vector. And this is your moment map, 1t square. You project it down to sphere. So when do you have a root? If this is perpendicular to this one. So that means that this intersects the plane with the normal vector in the direction u. So you want to count the number of times this intersects this, okay, this plane, and you want to take expectation. Well, if the coefficients are normally distributed, standard normally distributed, up to a constant, this unit vector is uniformly distributed over the unit sphere. So the expectation is actually taking the average number with respect to the surface area measure of this, but that's Crafton's formula that will give you up to a constant the length of the projectivized or a projected moment curve. So now the problem becomes a calculus problem, because we know how to compute the length of a curve, of a smooth curve. You need to integrate the length of the derivative, and that comes to this formula. So that's how this term actually popped up here. Okay, but this new approach, or rather this observation, the second line here, or the first line here, allows you to apply the same argument to different models. And the model is, okay, so remember, I was using the monomial basis with standard normal distribution or standard normal random coefficients AJs. Now what I want to do, I want to change the variance of AJs. Okay, it was 1. So if you change the variance to this 1 over the, the monomial or binomial term. So this model has already appeared in Michael Schub's talk, and the number of real roots, just calculating by the same formula, the expected number of real roots will be precisely root n. So if you use a different basis, right, rather than the monomials, using a new basis, so to speak, which is the scaled monomials, or in a different naming, if you change the variance of your random variables, then the number of real roots increase significantly from log n to root n. Moreover, this formula is precise. Okay. Well, the idea is just look at this object. This is, if you look at it carefully, this is kind of a Bergman kernel, which is the integral kernel of the projection coming from L2 to polynomials. And so if you compute its mixed derivative and integrate like in the formula, by binomial formula, this root n pops up and then you get the result. Okay, so far we have seen 2 models, and the first one looked more natural just using the monomial basis, but the second one has this intrinsic property that it's this new model, the second model, is invariant under orthogonal change of coordinates. So it has a more geometric model than the first one, and both models been studied intensively in the literature. So what we want to do, we want to generalize some of these results to higher dimensions. But when you go to higher dimensions, you have, of course, there's nothing stopping you to go to very high dimensions, but I will particularly talk about dimension 2. When you go from dimension 1 to dimension 2, there are at least 2 ways to generalize these results. Well, you can think of real roots as connected components. So one way to generalize is to look at the number of connected components of your algebraic curve or random algebraic curve. That's the one I will pursue today. Another way is to look at the length, and you can go from dimension 1 to dimension 2 is to calculate the projective length of your random real algebraic curves. That's been done in many other papers, particularly in this Edelman-Kostlin. And it's been observed that for the second model here, if you go to dimension 2, I will introduce in a minute what it means to have a 2-dimensional version of this model. They observe that the projective volume grows like n, and there is a precise formula again for the expected length of a random real algebraic curve in dimension 2. So there's a density, and you integrate the density and you compute the expected length. But for the second problem, there is no formula. So in other words, it's not known what the density of the expected number, or number of connected components of a random real algebraic curve. So there are estimates, and I will today talk about these estimates and maybe give you some motivation where these problems come from in real algebraic geometry. Okay, so let's start. Suppose you have a polynomial whose zero locus will be our algebraic plane curve. But throughout the talk, we are assuming that it's non-singular so that the components are disjoint, okay? And we know that this will be a compact one manifold, so the connected components of smooth real algebraic curve will be topological circles, okay? Now, when you have a topological circle in RP2, there are precisely two ways that it can sit inside. One is that it might have a connected complement. In this case, this kind of component is called a pseudoline. Second, it might have a disconnected complement, which means that topologically you can shrink it. And such components are called either two-sided or ovals, okay? And one of the classical problems in this sense, a deterministic problem, classify all isotopy classes, that is up to homeomorphisms, all algebraic, non-singular real algebraic plane curves. What are the number of connected components and how they are distributed in the plane? Okay, so this is the second part of Hilbert 16 problem. Now, what are the results known in this context? Well, if you denote the complex zero locus by ZF, it's a Riemann surface, okay, and its genus is given by this degree formula. It's an old result in real algebraic geometry that the number of connected components of a non-singular real algebraic curve is dominated by genus +1, and at least this much. So what does this say? If you have a degree, so I said that there are two options. You either have ovals or you have a pseudoline. Now, if the degree of the polynomial is an odd number, there's precisely one pseudoline for sure, and all the other components are oval. If the degree is even, all the components are oval and there is no pseudoline, okay? So this is a standard fact in real algebraic geometry. And furthermore, as a definition, if this upper bound is realized, if the number of connected components is equal to genus +1, then such curves are called M curves, where M stands for maximal, okay? Here's a maximal cubic. Remember, for degree genus formula, from the degree genus formula, we know that for a cubic, there might be at most two components. Because this is an odd degree polynomial, there will be one pseudoline and one oval. So I choose this cubic. It's a nice elliptic curve. And I plotted as zero locus in the plane. This picture is somehow misleading because I didn't plot it in RP2. Not possible. I sort of looked at the piece lies in the affine coordinates. So when you compactify, these two will get connected and it will be a closed curve. So it's better to look at the picture in the sphere. Look at this 2-to-1 natural map from sphere to RP2. Now, if you pull back the oval to the sphere, you will see two symmetric copies with respect to the antipodal map. This is typical. Whenever you pull back an oval to the sphere, you will see two of them. And this, when you pull back the pseudoline, you will see something self-symmetric. There will be only one copy sitting upstairs. Okay. So the problem now reduces to, because there is either one pseudoline or not. So the problem of counting the connected components reduces to basically counting the number of ovals. We need to count the ovals. And what about the probability structure? So let's go back to the beginning. How do I replace, how do I put a probability structure on the space? First, I take a real linear product. It's kind of a Gaussian, you see. So I put this probability structure on the space of all polynomials. This is the normalizing constant so that it becomes a probability space. Maybe I should give you a few examples. The first one is that the standard inner product. So this gives rise to Koch ensemble. The second one is this weighted either Schupp-Schmale or Adelman-Coston ensemble, where you define the inner product in a weighted way. This is multinomial terms. Okay, so here. So this gives rise to the generalization of this model to higher dimensions. And the third one, okay, so maybe here you could also observe that you could define the same inner product up to a constant, okay, by using the Lebesgue measure on Cm+1 and with this weight. So this basically shows you that there is a connection to weighted pluripotential theory, but I will not pursue that today, okay? So this point view. And another way to define, again, up to a constant, the same thing is just using the Fubini-Studi form on the complex projective space. So sometimes people refer to this ensemble as complex Fubini-Studi model, and there is a real version of it. It's defined in this way. So as long as you have an inner product, you will introduce this probability measure, the Gaussian type probability measure, and then you will ask the same questions. Okay. Now, a few minutes ago, I defined the maximal curves. The first question comes in mind that how often we see maximal curves. Okay, so let me introduce this set here. So those are the ones whose number of oval or number of connected components is bigger than genus plus 1. This is the maximum number minus some positive rational number times n. For n sufficiently large, it's known that this set is always non-empty. So there are always curves with a lot of real components. Okay, and the question is, how big is this set? The answer was given by Gaillet and Velchanger in 2011, that the probability of having a curve would, so we're talking about, first of all, this second model, complex Fubini-Studi on our list. Second model here. Okay, so the probability of having a curve in this ensemble with a lot of real components is exponentially small. Okay. For instance, if you wanted to have maximal curves, you can just put here 1 over n, and you could get an exponentially small probability. Okay, so they're exponentially rare. And this theorem is the one got me involved in this, because the techniques they're using is quite complex analytic. Okay, so let's see the idea of the proof. So what they do here is that, first of all, they observe that when you have a lot of real components, then for any complex ball contained in the away from the real locus of CP2, the genus of the complex curve intersected or lies in this ball can be bounded by its area. Okay, but then we know a theorem from complex analysis. I think this is due to de Talan, which says that if you had a cluster current of the normalized zero currents, 1 over n times the current of integration along ZFN, the limit current under this assumption would have a laminar structure. That means that it could be locally written as integration over analytic disks parametrized by a transversal measure. So the limit current would have a geometric structure. But we also know by Schiffmann-Zeldovich type of argument that these currents, these normalized complex zeros, converge to Fubini-Studi current, omega Fs, which does not have any laminar structure. So this basically tells you that whenever you have currents, whenever you have section or polynomials in this set growing with growing degree, then they will not converge. When you look at the corresponding complex zeros, they will not converge to Fubini-Studi. So it remains to establish kind of a large deviation, just look at a large deviation. What's the probability that you get away from the expected distribution kind of thing? And it's known that for Gaussian ensembles, that decay exponentially fast, and therefore you get the result. Okay, so whenever you have a lot of real components, the limit has to have a geometric structure, but we know that almost surely the limit does not have any laminar structure or geometric structure. So you're sort of comparing these two and asking, what's the probability that you get away from the expected distribution? And that's exponentially small. Okay, so that's the idea of the proof with one-page summary. Okay. So that's how they observe that this set should be small. And then, of course, the next question is that, okay, so maximal curves or curves with a lot of components are exponentially rare. What is the expected number of components? Like what shall we expect? Okay. And this took them a few years. I think in a series of papers, what they proved is that in any dimension, by the way, this is in any dimension, that the number of expected number of components grow like the degree over dimension over 2. So this is true in any dimensions. In dimension 2, therefore, the expected number of components grow like n. But as I said at the very beginning, there is no precise formula. There are estimates. Okay. How do they prove this? The upper bound is proved by using Morse theory. We're talking about 3 papers, so let's just say 1 sentence. And then the lower bound, this uses D-bar estimates of Hermander and Hermander's peak sections, together with a clever ideas. So what they do is that they take the real projective space, divide it into small squares of size 1/root of the degree. And then what they show is that with these small squares, whenever you have a smooth real hypersurface, it's attained as a 0 locus of a random polynomial with positive probability. And then they kind of show that the behavior in these squares are almost independent, so that actually each piece is sort of coming from a random polynomial. And combining all this together, they show that with positive probability, you get a lot of components. A lot of means n. So that's their thing. Again, vaguely explained. It's mid-sized paper. So that's the essence of their argument. Okay, so so we know that now the expected number of ovals, because the pseudo line thing is just +1 or not. So the expected number of ovals grow like n. Okay. Now these pictures are taken from the net. I think they're due to Buffera from Grenoble. So basically, a computer chooses a random polynomial from this Edelman-Koston ensemble, the second ensemble, and plots the regions where they are positive and negative. So I think the blue color is positive, green color is negative. So the boundary is our algebraic curve. So this is degree 500 polynomial and 1,000 and 10,000. As you see, the picture gets complicated fairly quickly. And we want to say something as the degree grows to infinity. Okay, what was our questions? First question was, what are the expected number of ovals? Okay, it grows like n. The second question was how they are situated. This is quite vaguely stated. Maybe we can make it precise by saying something like this. Maybe we can count the number of nested ovals as a starting point. So given a point in your sphere, what would be the expected number of ovals which are containing this point in their interior? So what's the expected depth of a random dual algebraic curve at a given point? Another question would be, so I see a lot of small components here. Are there big components? So comparing with this argument or the proof of Gaia-Welchanger, so when you divide your RP2 into small squares, are there components going out these squares and travel around? Are there big components? I think I will be able to answer this question at the end. So let's start. My apologies, I forgot about this slide. So the second, okay, so in the proof of Gaia-Welchanger, the second part I said the lower bound using D-bar estimates and so on. So that actually that idea appeared in the paper by Nazarov and Sorin in 2009 when they studied the number of nodal domains of random spherical harmonics. And at the beginning I mentioned the third model, the real Fubini studi. What is the expected number of components for the third model? Well, in this paper, they computed, Berario and Lundberg computed the expected number of components. In dimension 2, this would be n square. Okay, so it grows much faster. Okay, so we have three models, the Hodge model, which I will say something at the very end, the complex Fubini-Studi, and the real one. And the real one has a lot of, has more ovals. Expected number of ovals is growing at a higher rate. Okay, so now going back to my question. So can you say anything about how these ovals are situated in RP2? To make it precise, given a point P, what is the expected number of components of a random real algebraic curve that are winding around the point P? Okay, so here's the hypothetical picture of a random real algebraic curve. I cut it off at infinity, looked at the piece lies in the affine coordinates. That's my point. So there is one curve, there is two curves, there are three curves winding around this. But when you actually connect these two, when you compactify, there'll be fourth one. Okay, so I want to count the number of components winding around P. This defines a random variable here, LP, from my space of polynomials with this second model, the complex Fubini-Studi model, and I want to compute its expected value. Okay, so starting with our polynomial f, writing it down to in this form, these CJs will come from my inner product. So if I work with the second model, this will be multinomial coefficient here with square root. And these AJs will be the independent copies of standard Gaussian N01. And here's the formula. So what I do here, maybe I should say a few things, right? So before I move on, I identified a point P in RP2 with the origin in the affine chart. And so I will give the formula in this affine coordinates that the expected number of connected components of a Gaussian random real algebraic curve in this form here, right there, is given by this formula here. So the formula is obtained by sort of pursuing the ideas of Hodge, the original argument, and it's given in terms of this form here that is familiar from complex analysis that you would use to count the number of winding number of a curve around the point at the origin. So the expected number is calculated as a double integral, where you have the expected value of the conditional derivative, or conditional expectation of the normal derivative, the size of the normal derivative given f is equal to 0. And then there is a number appears here. Okay, so I will talk about the proof, but what is this number? When the degree is even, all the components are ovals. So we have a precise formula when degree is even. And when degree is odd, I told you that there's one pseudo line, and this is the contribution of the pseudo lines. Okay, and we know that no matter what n is, this number is at most in absolute value is 1/2. So this piece here and gives you the growth number of expected depth. Okay. So a few words about the proof. So what we do is that we kind of, I said, we kind of pursue the ideas of Hodge. So what we know is that consider a smooth real algebraic curve of degree n in RP2, such that the line at infinity, let's call it z is equal to 0, is not a component of VF. That's almost surely the case, because otherwise it's an algebraic condition and our probability measure does not put a mass on. So that's generically the situation. And assume that the equation of VF in the affine chart, z is not equal to 0, is given by above formula, the 2 slides before. Then the number of ovals of VF containing the point at the origin in its interior given by this formula. So we are basically getting a counting lemma for the number of ovals containing the point origin in their interior. This formula is precise when degree is even, and the formula adds something that comes from the pseudo line when degree is odd. And again, this number is bounded, and that's the number appears in the expected formula. Okay, when you take its expected value, you get something, but it's not big. Okay, the idea is similar, but this time we have to look at f itself and its normal derivative. So, what Kutch was doing is that because this transversal intersections, he was just looking at the change in the derivative. So what we do here, we take our one form and bump it in the normal direction, complete it to two form, so that we can play a similar game. Okay, so that's what we did here. So our random variables now f and this normal derivative. And if you do the calculation, in other words, it's in a similar way. When you have a counting lemma, what you want to do, you want to compute its expectation inside, and then using integral theorems, you want to sort of switch the order of integration and expectation. And that's what we do here. And so once you switch the order, you end up with this term. Looks like complicated, but if you look at it very carefully, you will see that it's again the mixed derivative, the log of the Berkman kernel with respect to these kind of differentials. So that's the result, gives you expected depth of a curve at the point P. And if you apply the formula, let's see, if you apply the formula to this complex Frobenius-2D ensemble, it gives you that for every point P in RP2, the expected depth of your curve will be of order root n divided by 2 plus a constant. This constant is the constant in the formula. So it's 0 if n is even, and it's less than in modulus 1/2 when it's odd. So we have a formula for the expected depth. And the idea was just using the, computing the Berkman kernel. And once you plug in the Berkman kernel into the formula, then you use binomial formula or multi variable version of binomial formula, and this comes up. Okay, any questions so far? Okay, so I think at the beginning I said that the model is so nice that it's invariant under orthogonal change of coordinates, and that's why the right-hand side does not depend on the point P. So this, for any P, you have this many components containing that in the interior. And with this result, so at the beginning, I said that we know the expected length of a random real algebraic curve. It grows like n. The number of connected components grows like n. And we know that that many of them are nested at a point. So with this, we can prove that with positive probability, there are ovals that can't be contained in these small squares, 1/√n. So there are large components. Okay, and that was, I think, all I wanted to say.
So any questions?
Thank you. Very interesting talk. So I'm not a specialist at all. So my question maybe. So there is this Milnor bound on the connected, the number of connected component of 0 of polynomials. And there were this work after of Kovansky looking at phenomials, so polynomial with few coefficient. So would you be able, or do you know if there are results on the expected number of connected component of
for
this?
phenomials?
Yeah, for phenomials.
Yeah, I don't know.
It seems to be a very interesting question for practical aspects.
Yeah, I know recently people are looking at phenomials. I've seen results on and some results on expected or probabilistic results on real zeros, but I'm not sure about because the techniques here, the Steve-Bar techniques and so on are you can't, so because you want to control, you want to control the degree. Not only that, you want to control the Newton polytope of the thing you are creating, and that might be the difficulty. So with this, Hermann's peak sections or D-bar estimates, you know that you can create polynomials of large degree with certain number of components, but the object you are constructing, you want to have a specific number of terms inside, and that might be the difficulty to control. So with these techniques, I'm not sure, but maybe with other techniques, it would be interesting to look at, for phenomena.
Can I ask a second question? Sorry. And if you look at, instead of looking at polynomials, if you look at gradients, same question.
Yeah. I think there are some works by Lerario, maybe Lundberg. Those are the people. I believe some results, but I don't know about the details.
Quantities.
Yeah.
Okay. Thank you.
Yeah.
So in this first model where you don't have the unitary invariance, so do you know the dependence on P of this expectation?
Yeah, good question. I'll know a few things. It's in this this paper. So for that model, we computed the expected number of curves containing the origin inside. And it was something like, but with an assumption on the Newton polytope. It wasn't precisely the Koch, but with the Newton polytope is square. So degree D means you're allowing x to the d, y to the d. Okay. With that, we computed the expected depth at the origin. It was log of the degree. So that tells you that the number of components should grow faster than log d, but the precise growth is not known.
And if you change the origin to other points, you can
if you change the origin to other points, you get less. But what we also know from complex analytic side, the zeros are accumulating around the complex torus. So looking at around should give you the approximate answer, but the precise answer is not known for the big problem.
Okay. And another question: are there any general results in higher dimension?
This paper actually, this paper these Gaia-Welschange papers are written in higher dimensions in this complex notion. Okay, so you have a real, you have a complex manifold with a nice real locus, so CPM, RPM, and you have a real holomorphic line bundle over it, and then the results are about the holomorphic section, global holomorphic sections, as the tensor power grows. So all the results are in that setting, and they are in any dimension.
But this laminar current stuff, it's usually
okay. So what
harder.
about the first theorem? I think no. This one, you see this laminarity thing.
Yeah.
Okay, so the Talon has higher dimensional version of these things, woven, blah blah. I'm not. I looked at it, but I think it's not going to work. So let me just speculate, okay? So because the same kind of argument would say, okay, so you have a limit, would you have a woven limit and so on? But wovens are more flexible than laminar. So, yeah.
Actually, I have a question. So these, the ovals, they sort of decompose I guess it's really the complements of the ovals have a kind of tree structure to them in the sphere. You have vertices or components, and edges or adjacency, and so you get a random tree.
Yes.
Out of this.
Yeah,
and what you're doing is in that direction.
Yeah. So the big question we don't know how to answer. What's the expected tree? What do you expect to see as a picture, as a topological picture? We're very far from that, but I was trying to quantify the tree, putting some sort of like when like putting an energy type of thing, like if you do JSON and then if you have separate branches you add and otherwise you multiply, things like some interesting quantities, like what would be just quantify the problem.
You could ask about how much branching is
something like that. I could get some results, but they're not leading you to sort of like you also want to go back, right? So if you have a maximum quantity, you want to have a certain topological picture, things like that. So one result, okay, I don't know well, anyway, so not to go into further. So I was trying to quantify the problem, some partial results, but it's not clear what am I going to do with these quantities, because at the end you want to say this topological picture corresponds to this quantity, but there's nothing like that yet.
I see. Anything else?
So I'm a little bit late, so I maybe didn't get your first part. So you say the components of an algebraic curve will be either pseudo line or ovals.
Well, for degree odd, there is precisely one pseudo line. All the others are oval. For degree even, all of them are oval.
Okay, and when you say oval, you mean that it has the canonical equation, or it just kind of some homeomorphic?
When I say oval, it's you can say it's you can shrink it to a point, so topologically trivial, or it has a trivial class in homology, or you can say it has two connected complement components. So there's inside and there's outside.
Okay.
Thanks. And thanks for inviting me.
It's a very pleasant form of exercise here.
Yeah, thank you for the talk. Yeah, so I was just wondering how you distinguish the inside from the outside.
These are real algebraic geometry questions, I guess. The inside is topologically equivalent to a disk, and the outside is Möbius band.
Oh, right. Okay. Yeah, thank you.
An example coming from topology of such a quadratic form. Then I give an geometry. Then I'll discuss the theorem on the signature. And to justify it, I will give it a classical application. Oh. And finally, we'll discuss this conjecture. Okay. So let's consider a topological manifold, which I mean compact, connected, and oriented. And to such an object, we have the cup product. We can associate the cup product. Okay, which is defined topologically, and if you want to compute singular cohomology with, for example, differential forms, this corresponds to wedge on differential forms. Okay, and in the special case when the dimension of X can be divided by 4, then there is an interesting quadratic form to study in the middle cohomology. Okay, of course, you can consider the middle cohomology also when the dimension is even but not divisible by 4. But in this case, this pairing will be alternate. So in order to have really quadratic form, you need to consider this dimension. Okay, and it turns out that okay, so this is a non-degenerate Yes, it's everything is topological for the moment. So it's dimension, yeah, it's a real if you want. So it's a non-degenerate quadratic form over Z. Okay, and non-degenerate is part of the Poincare duality. Okay, and this is actually a very fine invariant of such a geometric object. And let me recall an application. So you can use this quadratic form to show that there are such X of dimension 4, which cannot admit a C-infinity structure. So there are topological manifolds which are not differential manifolds. And the point is really to use this invariant. Let me recall how. Okay, so this is a combination of two theorems from the 80s. One is due to Friedman, and it says it's a construction theorem. It says that to any reasonable quadratic form, you can associate a topological manifold realizing it. So for all pair MQ, so this is an abelian group of finite type, and this is a non-degenerate pairing on it, Z quadratic form. To any such a pair, you can construct a topological manifold of dimension 4, such that the middle cohomology and the quadratic form corresponding to it is just this pair. Okay, so topologically there are no restrictions. But if you go to now to differential geometry, now there is a restriction, and that's the PhD thesis of Donaldson, again in the 80s. So if X has dimension 4 and is a C-infinity manifold, and if this quadratic form is positive definite, then it is diagonalizable over Z. And of course, the strong restriction is exactly over Z. Of course, any quadratic form can be diagonalized, for example, over Q, but over Z, it's a real restriction. And of course, as there are such a quadratic form which are not diagonalizable, then there are C-infinity topological manifolds which cannot admit C-infinity structure. Yeah, so let me give an almost example of such a quadratic form. If you consider this one, so this one over Q or over R, it's the same as this one, but not over Z. And you can see this. So let me call this Q1, and this is Q2. You can see this because the image of Q1 are all the integers. You can, of course, realize all the integers as xy. Whereas if you look at this one, so this is xy, x square minus y square, then modulo 4, the squares are only 0 or 1. So you cannot obtain 2. So the image of Q1 is not 2 modulo 4. So they cannot be the same over Z. Okay. Why is this an almost example? Because it's not an example of positive definite. If you want an example of positive definite, then you have to go to dimension 8. So it's rather complicated to write down, but there are. Okay. Questions so far? Okay. Let us now play the same game with algebraic geometry. Okay. Okay. So here, I will replace topological manifolds with algebraic varieties and singular cohomology, so simplices to sub-algebraic varieties, so what is called algebraic cycles. And the cup product will be replaced by the intersection product. So to justify this, let me recall the theorem of Bezout, which is the starting point of this theory. So let C1 and C2 inside P2 be two algebraic curves. Then the intersection product, sorry, the number of points in the intersection is equal to the degree of C1 times the degree of C2. Okay, let me draw some pictures. So if you consider number of points of intersection of two lines, then you find 1 times 1. A circle with a line, then you have 1 times 2. And maybe 2 quadrics, then you have 2 times 2. Okay. But okay, one has to pay attention, of course, in this statement. You can have 2 parallel lines, and for which it is very important to compactify the situation looking inside P2. So you have 1 infinity point. You can, for example, consider this intersection of 2 circles, which is a very common picture. And here you see only 2 points. And the point is that you have to compute also the solution, the complex solutions, for example. So the solution is the algebraic closure of your field of definition. So here there are 2 points with the complex coefficients, which are exchanged by the complex conjugation. Okay, and then there are also other subtleties. For example, you can have a picture like this. And here you see 3 points. And the point is that this one has multiplicity 2. So you also need to define a notion of multiplicity in the intersection. And okay, maybe the most important one is that sometimes C1 is equal to C2. And here, of course, you have too many intersections. And now you need to deform a little bit one of the 2 equations to make sense of the intersection. So this, and you need to deform to something like this. Deform. You have to move a little bit one of the equations. Okay, so with these subtleties in mind, that's precisely the statement of the theorem of Bezout. Okay. And what the intersection product does is a generalization of all these for varieties which are different from P2. Okay, so we will fix a base field, for example, C. And we consider an algebraic variety, which I will mean projective, smooth, and connected. So we saw examples in the previous talks. This means given by equations inside the projective space, which are homogeneous. These are defined by polynomial equations. Okay. And so some of to such an ambient space, the analogous of what was singular cohomology will be now this space. So it's the Q vector space generated by all subvarieties of codimension A, modulo what is called the numerical equivalence. So it's in some sense it's similar to what you do with the singular cohomology. You take all simplices, so it's a very huge vector space, and then you mod out by a reasonable relation, and this will give a computable invariant. Okay, so this space before the relation is very huge, and then you have something reasonable. So I don't want to recall what the numerical equivalence is, but I will give the main properties. So first, these are finite dimensional spaces. If you can deform two subvarieties, then the class will be the same. And of course, we need this from Bezout. All points are the same. Equivalent, which means that the maximal codimension group is just one-dimensional. Okay. Oh. Then I have an intersection product, which looks like the cup product. And why is it called intersection product? Because you really associate the intersection whenever this is transverse. If transverse. So what does it mean, transverse? Something like this. And of course, as we saw in the examples, for example, this one, when the intersection is not transverse, you need to associate also some multiplicities. So it's more subtle. Okay, but if it is transverse, you really associate the intersection. And the codimension, of course, goes in this way. Okay. Okay, and the final and probably most important property is some analog of the Poincare duality. So this is a perfect pairing, just as in Poincare duality. Okay, so let me give an example. If we take P2, then what are these groups? So if you want something of codimension 0, there is not much choice, there is only P2. So this is all this Q of the class of P2. It's one-dimensional vector space. And then if you want something of maximal codimension, then it's property 3, then this is just, again, it's again one-dimensional, and it's the class of any point. And what is special for P2 is also that this one is one-dimensional, and the map is to a curve of degree d, you associate the number d. And under this identification, the theorem of Bézout is equivalent to the following statement. So the intersection product so taking two curves and intersecting in the counting the number of points at the intersection, then this map is just the multiplication. But for varieties which are more complicated than P2, this intersection product will be richer. Okay. Okay, other questions? Okay. Okay, so this is the invariant we'll look at. And let me give a theorem on the signature. So the classical theorem of Segre says the following. So let us take an algebraic surface. So an algebraic variety of dimension 2. Then the intersection product. So you take curves inside S and you count the multiplicity of the intersection, the number of the intersection points. This is of signature. So the positive part is 1 and the rest is negative. Okay, so there is one positive and the rest are negative. Let me give some examples. So if you take the surface to be P2, then we computed the intersection product, and this is just one dimension, and we found indeed something positive definite. Maybe something less trivial. If you take P1 cross P1, then you can consider a vertical divisor and an horizontal divisor. So the point you pick as a first coordinate doesn't matter because all points are equivalent. So you have a vertical divisor and horizontal divisor. Let us now compute the intersection. If you compute V times V, then you can change the point. So now you have two vertical lines and there is no intersection. So this is 0. And similarly, H times H will be 0. Whereas if you compute V times H, then you have a picture like this, then you have 1. Okay, so in this case, the intersection product corresponds to this quadratic form, which is of signature 1, 1. Okay. So somehow the relation you put forces some negative intersection appearing. Yeah. Okay, which is maybe not very intuitive when you think of the number of intersection, but it's forced from the relation. Okay. Okay. Okay, let me give a remark. So if the characteristic of the field is 0, you can, if you want to show this theorem, you can reduce easily to the complex numbers. And in this case, and one can use the so-called cycle class map. Which takes a curve, an algebraic curve inside the surface. So now if we think topologically, the surface has dimension 4 and the curve inside has dimension 2, if you think topologically. So we can integrate two differential forms. Okay, and this will define a dual element on differential forms. A linear map on differential forms, but okay, by Poincare duality, it's the same as each H2 himself. Okay, so you have a way of associating to an algebraic curve a differential form, a class in the RAM cohomology, and through this you can compute the signature here on this side. So you can compute the signature using differential forms. Yeah. So this cycle class map, you can check that sends the intersection product into the wedge. And so it's really a question about wedging differential forms. Okay, so if you're in characteristic 0, you can prove this theorem in an analytic way, and that's actually an argument due to Hodge a few years before. But if you want to show this theorem for any field, then you need an algebraic proof, and this was given later by Seger. Okay, so if the characteristic here is P, so for example, this field or this field. So F9 is constructed from Z3 just in the same way as you construct complex number from the reals. So if you take these maybe exotic fields, then one needs an algebraic proof. Okay. Questions so far? No. Okay, so let me now explain why one cares about such a signature theorem. So let me give an application. Okay, so let me start with an example. So let us consider this equation. And one would like to compute the solution, say, for example, in the field Z over PZ. Okay, and if you want to do this for a given prime, for example, 3, this is very easy because you just write down all the possibilities. And okay, if I replace 0, I obtain 0. If x is 1, I have 2, and if x is 2, I have 10. And then I just add 1, and I add 4. Okay, so you can really make the computation, but as we want to look at solutions modulo 3, of course, this is a solution, but there is also this one and this one. So there are 3 solutions. Okay. So what these examples suggest is that if you want to compute solutions for a given prime, it's kind of a straightforward thing to do, right? You just write down all the possibilities and you compute. But what about for all primes? If you want to understand all primes at once, then this is subtle now. You cannot just make the list for each for all primes. And this is a classical theorem of Hasse, which says that the number of solutions modulo p is more or less p, as in this case. And the error term is 2 times p to the power 1/2. So there is an error term. And let me say that this 1/2 is intimately related to the Riemann hypothesis. It's the analogous of the Riemann hypothesis for finite fields. And it's for finite fields, it's known, it's a theorem, it's not a conjecture. Okay. And I would like to give a generalization of this theorem, which is due to Weil. It says the following. So let us consider an algebraic curve, which is again in my convention smooth and projective, and suppose it is of genus G. I will say in a second what genus G means. Over some given finite field. So for example, this one, but you have to compactify to homogenize. Then the number of solutions over the field of definition is more or less the same as the number of solutions of the projective line. And the error term as a constant which depends on the genus. And then there is again q to the power 1/2. Okay. So here there is a 1, which is not here, because here I just considered the affine equations. And if you go to the projective space, there is 1 extra point. So this statement is really the generalization of this one. Okay, so what does genus mean? So I don't want to give the general definition, but let me give 2 examples. So suppose that your curve is inside P2 and is defined with an equation of degree d. Then there is an explicit formula for the genus. So for example, if you compute in that case, you find 1. It's degree 3 and you find 1. And a second case is that, okay, your curve is maybe the reduction modulo p of something in characteristic 0. And then you can look at the complex solution. So it's exactly what happens here. Of course, this equation makes sense also in characteristic 0. And then you can look at the complex solutions and you will find the Riemann surface. And here the genus is the topological genus.
So it's implicit in this that the curve is smooth?
Yes, yes, sorry. In my conventional, in my conventional algebraic variety, I take smooth and projective. Everywhere I consider smooth and projective. Yeah. Thank you. Hasse is genus 1. Hasse is genus 1. Yes. I just wrote on an explicit example to give some computations, but genus 1. Okay. And okay, what I would like to do is to give a proof of this theorem, but not the original one, the one given, so proof, the one given by Grothendieck. some years later, which is based on the positivity, on the signature theorem of Segre I gave before. Okay, so the theorem of Segre was a theorem of about intersecting curves inside the surface. So let us give what the surface will be. It's C times C. And let us consider the following curves inside S, sorry. Inside S, we consider a vertical divisor, a horizontal divisor, a diagonal, and then the graph of the Frobenius. So we erase all the coordinates with Q. Okay, let us compute the intersection product. So we already computed V times H, V times V, and H times H. That's the same computations there as before. Then you can compute V times diagonal. And here you find 1. And then V times, sorry, horizontal times diagonal. Again, 1. And then diagonal times diagonal. And this is the non-trivial computation. Probably. This kind of computations appear also in topology. And what appears to be is the Euler characteristic of the variety. So here you have 2 minus 2g. Okay, that's the non-trivial part. And then we compute the graph intersecting with the vertical. And this is 1. And then the graph with the horizontal. And now this is the degree of the map. Which is Q. Yeah, if you intersect with the horizontal, that's the degree of your polynomial. And then the graph is intersecting with the diagonal. So, but when we have a map, what is the intersection within the diagonal of the graph? Well, that's the fixed points. And by Galois theory, what are the fixed points? Well, that's precisely the solutions we are looking at. That's the solutions defined on our base field. Solutions defined on our base field. Okay, and then the final computation is this one, which can be obtained from this one. Maybe I don't explain this. You can deduce this one from this one. Okay. Okay, so for the moment, we just played some game and we just wrote down a surface, computed some intersection. So what about now this? This statement? Well, there is a little miracle appearing. If you compute the determinant of this 4 times 4 matrix of all these intersection products, then what you get is precisely what you're looking at. Okay, and then now your goal is to show that the determinant is non-negative. Sorry, no, is not positive. Okay. And okay, let's show this. So if the determinant is 0, then okay, we are done. And if the determinant is non-zero, well, then it means that if you consider the vector space given by these 4 classes, inside our space of curves inside S. Okay, if the intersection product is non-degenerate, then this means that this space is of dimension 4. But we know the signature on all the space. The signature on all the space is one positive, the rest negative. So this means that the signature on our space E has two possibilities. Either is 1, 3, either is 0, 4. There are no other options by this theorem of Segre. Yeah. As we know the signature on all the space, then we can deduce the signature on the subspace. Okay, that's where we use the Segre. Okay, and now if the signature is 1, 3, then the determinant is negative, and then we win. And if the signature is 0, 4, we lose. So now we have to look for a vector which is positive. But we already know one. It's v plus h. We already produced something positive. So on the other hand, v plus h is a positive vector. So we are done. Okay. Other questions? This one or this one? This one. This one. Okay. So you are computing the intersection of this map with this map. And what is this? It's precisely the set of x such that f of x is x. So the fixed points. And now this map is the Frobenius. And by Galois theory, if you take all the points which are fixed by Galois, these are precisely the points defined on your field of definition. Yeah. Okay. Sorry, I wrote C, I meant. Okay. Here I consider all the points in the algebraic closure, if you want. And so I'm looking at the points in the algebraic closure fixed by the map, but the map is the Galois group. So these are precisely those defined in the field of definition. Thanks for the questions. Are there other questions? Okay. Okay, so this is the reason why Grothendieck got interested in such a signature statements, and in the remaining minutes, which is how much? 5? 5. I will say a word on this conjecture of Grothendieck. Eight? Okay. So this is called the standard conjecture of a Hodge type. Okay, and that's a conjecture of Grothendieck, which was formulated in the 60s. So we take an algebraic variety. Of dimension, say D. So here again, I mean smooth and projective, and let us denote by rho A the dimension of this space of cycles we already studied. And then we can consider, sorry, maybe D is not a good idea. Sorry, 2D, sorry. And then we can consider a quadratic form, which looks like the ones we already found on the middle subvarieties. So here we go to points, and points are all equivalent. So this is now a quadratic form on the middle cohomology. For example, we studied the surface and we intersected curves inside it. Or you can take a fourfold and intersect surfaces inside it, these kind of things. And then the conjecture is that then its signature is so let me first give the easy part. What is the signature of the S minus? Well, it has to be the total minus the plus part. And then what is the plus part? Well, it's an alternated sum. But it goes up to the biggest even number before D. Okay, so let me just write two examples. If you take D equal 1, then the signature should be 1, rho 1 minus 1. And if D is 2, then the signature should be and so on. Okay, when one sees this formula for the first time, it's completely unclear why this should be reasonable. Okay. Let me say what is known. Well, first of all, the case of surfaces. So the D equals 1. That's precisely the theorem of Segre we already saw. And then maybe the most important evidence is that this is known for in characteristic 0. Because again, in this case, you can reduce to the complex number, and we can consider again the so-called cycle class map. Again, by integrating, one takes a subvariety and associate the integration on the subvariety. And this cycle class map sends intersection product to wedge, to the cap product. And one computes the signature of the latter. Explicitly with the differential forms, what is needed here is Hodge theory. And the so-called Hodge-Riemann relations. Okay. So I guess what Grothendieck believed is that okay, there is an a purely algebraic statement which is true in characteristic 0. Then the same statement should be true also in characteristic P. So as the statement is algebraic, it should be true also in characteristic P. And okay, so then I proved it. for X being an abelian fourfold. So something of dimension 4, which admits a group law in positive characteristic. And okay, maybe I'll say just a little word and then I stop. And here the problem is that these real quadratic forms, so in positive characteristic, this real quadratic form does not have a cohomological interpretation. Which one has through this map in characteristic 0. So you don't have something like this in positive characteristic. And somehow the solution is to first study the other completions. Because they do have cohomological interpretation through Ladic and crystalline cohomology. So one can study the other completions, and then one can deduce the real part through some product formulas. So there are product formulas which relate when one starts with the quadratic form over Q. There are classical product formula relating these completions with this completion. So through this product formula, one can deduce this one from these ones. Okay, let's stop here. Thank you very much.
Any questions? Yes.
In that conjecture, S plus should be always positive, no?
Mm-hmm.
And can one prove it is positive?
So yeah, so it's not clear from this way of presenting things, but actually the these numbers grows up.
You don't use any Hodge theory?
No, and this is but okay, but yeah, let me say why. The reason is that there is an injective map which is obtained with by intersecting with an ample divisor.
Then non-degenerateness.
Yes. Yes.
Thank you. Thank you.
Welcome.
Anyone else?
And for the proof, where do you use that it's abelian and where do you use it's a fourfold?
Yeah, so thank you very much for the question. So these product formulas, these are something classical. It's called about the Hilbert symbols, maybe. So for example, in France, we learn with the Serre's book on arithmetics. And the problem is that this product formula gives a complete control of the signature only if the quadratic form has dimension 2. Otherwise, you also only have partial control. So in reality, the point is not a question about the variety, it's a question about the quadratic form. And now you have to look at varieties having this kind of property, and there are none. And then you have to work a little bit more and say, okay, maybe I cannot find something of dimension 2, but I can find something which can be decomposed in quadratic forms of dimension 2. And this is the real condition one should look at. And that's where somehow the hypothesis come into.
When you say product formula, I think of number theory, like the product of
Yes.
It's in the same sense.
Exactly the same sense. So it's, for example, if you take a rational number, then the product of the absolute values with the classical one or the p-adic ones, it's 1.
Yeah.
And this precisely is telling you that if you want to compute the classical absolute value, well, from this formula, you can deduce it from the p-adic ones. And then you have something similar for quadratic forms, where instead of the absolute value, you have Hilbert symbols.
Another question. When you say there's no cohomological interpretation,
Yes.
Meaning none is known, or there just really can't be one?
That's a very good question. So somehow both, in some sense. So Serre in the 50s showed that there cannot be a cohomology with real coefficients. So this is for sure. Whereas Scholz recently proposed a conjecture, like it was in the ICM, there should be a cohomology with C coefficients. And okay, if one can construct one day this cohomology, then probably there will be an interpretation of this.
Thank you. Other questions?
So in your Hodge type conjecture, you only look at a variety of even dimension?
Yes. So it's just to go faster in the presentation, but it's equivalent to the classical one. Yeah, maybe I can explain you later, but
okay, no problem.
Okay, I raised it, but okay, the conjecture which was here is precisely equivalent to the classical one. This formulation is faster to given, so it's better for talks, but it's less understandable. So of course, this strange formula with the sums, it's unclear. So that's why one studies the other formulation rather.
Thank you. Thank you.
Yeah.
I'm sorry to monopolize, but so if the conjecture were true, you get some sort of statement about counting rational points?
Yes. So if one follows the same argument of Grothendieck before, then the standard conjecture of Hodge type for x cross x. So before we were using C cross C. Now, if you can show the standard conjecture of Hodge type for x cross x, then you have what is called the Riemann hypothesis for x. Okay, but okay, so this is again the same argument of Grothendieck. But then, okay, there are two problems. First of all, for example, in the theorem, in this theorem, I definitely use the Weil conjecture, the Riemann hypothesis. So it's not a new proof. And second, also the Riemann hypothesis is now known since 50 years. So maybe there was an alternative proof due to the linear. So maybe this kind of applications is no more interesting.
Oh, I see.
So it's already known nowadays since some time. Yeah, exactly. So.
But you're literally counting solutions and characteristic P.
Yes.
Okay.
And then the estimates, before there was the genius, and now the estimates is through the Betti numbers. Yeah, it's precisely the same statement. Yeah, thank you very much. So Saito showed that this implies the monodromy weight conjecture, which is open. So yeah, maybe this is an interesting application.
Other questions? Thank you again.
Yeah, thank you very much.